Everyone, so we're going to do problem 9-59 right now. So what we have this 40-foot stretch of railroad tracks, and two different spaces have been made in the rails to allow for thermal expansion when the outside temperature changes. And we're given that the initial temperature is 20 below, and that the second temperature is 90 degrees Fahrenheit. And using those two, we have to find how big the gap is. And then once we know how big the gap is, when the third temperature goes above the second temperature, we're going to actually be past that gap because of the higher change in temperature. And that's going to cause the rail to actually push back a little bit. And they want to know the actual axial force in the rails when the temperature goes up to 110 degrees Fahrenheit. And they give us that the cross-sectional area of each rail is 5.1 inches squared. So the easiest way to do this is obviously you got to draw your diagram, but instead of worrying about two gaps, you're going to want to imagine that this one, let's close it up, and we're going to make this one twice as big. It's the same difference. In reality, we would find the total thermal expansion of this middle piece, divide it by 2, and that's how far they go on each side. But for simplification of calculations, it's easier to take a section right here, if you will, and then multiply this gap by 2 to allow for what we're missing over here, and think of it as expanding in only one direction. So over here I drew my picture with all the relevant information here, and so we're going to find out how big that gap is. So the displacement due to thermal expansion is equal to the alpha coefficient times the change in temperature times the length of whatever specimen we're looking at. And this was A36 steel, and the alpha coefficient for that ends up being 6.6 times 10 to the negative 6 per degree Fahrenheit. So once you multiply all that out, you're going to get 2.904 times 10 to the negative second feet. But since they give us the area in inches squared, I thought it would be easier intuitively to convert this to inches. So once you multiply that by 12, you end up getting 0.348 inches, and that's how big our assumed gap, that is double what is shown, is. But in reality, we would divide this by 2, and that's how big each of these are. But remember, I said that we're going to, in essence, take a section here, and we're going to multiply this gap by 2 and assume that it only expands in one direction instead of both like it would in reality. So like I said, like we've done, we have 0.348 inches is equal to the total displacement. So now, once we go up to 110 degrees Fahrenheit, we want to figure out the axial force in the rails as a result of the longer elongation of the rails past that gap. So that's going to involve the old axial force equation that we had, the PL over AE, which in reality we can just substitute P for F. So let's think about this. So the displacement total, once we go up to 110, we're gonna go to 90, go to 90, go to 90. It's gonna expand. It'll touch, and then as we keep going up in temperature, the thermal expansion part of the displacement is going to keep pointing right. But because we're going to be pushing into this part right here, that's actually going to point left. So total displacement is going to be equal to the thermal expansion displacement minus the displacement due to the axial force. And this is really as simple as just a plug and chug, really. So we're going to solve for force. This is just multiplying, subtracting, and dividing. And then, so you literally just substitute everything in. We found displacement was 0.348 minus, this was already calculated earlier. You're gonna have to convert your feet to inches, obviously, times your area, times your E value they give you, divided by your length, and you end up getting 19.7 kips, and that's your axial force.